So one of the ideas that you mentioned is your work in asymmetric chip multiprocessors, which probably people know more about as multicores and heterogeneous multicores. So,
those are all the right buzzwords.
right. So why is it important to have cores that are not alike, cores that are different capabilities on a chip?
Yeah, so there are, companies, so I've been talking about heterogeneous for a long time now. It's been, I came up with the notion, well, probably wasn't the first one, but it hit me, in fact, it hit me in a talk I gave at Illinois back in 2002, so that's 12 years ago, that you really want heterogeneous cores. And at that time, in fact, up until about a couple of years ago, all the multi-core chips, multi-core, as you know, a core is a processor. In the old days, the chip had one processor on it, so it was, a single core. They didn't call it cores then, they called it processors. And then, and in fact, I don't know why they call it cores, but we seem to be stuck with that in our lexicon. We then went to two cores on two processors on a chip, and 4 and 8. And it's easy to do if, in fact, they're identical. Because when you do the design, you do one design, and you bump, bump, bump. It's like a cookie, making cookies with a cookie cutter, They're all identical. So it's cheaper because you only have to design it once. If you do heterogeneous, if each one of them are different, then it's not so easy because you have to have a design team doing one, a design team doing another, and a third one. And you say, well, does that make sense? Well, I got a couple of analogies for you. Many people have a machine shop in their basement where they do carpentry and fix things and fix your car and all that. And you need a set of wrenches. Well, you don't really need a set of wrenches. You could have just one wrench, adjustable wrench, right? And then you just set the adjustable wrench to whatever setting you need. What if that bolt is rusted on? The adjustable wrench, with slippage, you'll never get it off. But with a set of wrenches, each wrench has an individual size opening, and you need the one of the wrenches for the particular bolt. And there are many different bolts, and so you need many different wrenches. You could get away with a single wrench that's adjustable, but it wouldn't work as well. And that's always the case, that if you have something to design for a specific task, you'll do much better on that task. Problem is, of course, you can't do any other task with that. So the wrench that has an opening of 1 inch is useless on a 2-inch bolt or a 1/2-inch bolt. Don't work on either. It only works on the 1-inch bolt. But it really works on the 1-inch bolt. So if you want to optimize the performance, you need something tailored to it. Another example is, I gave you one football analogy. Here's another football analogy, right? So how many quarterbacks do you want on the team? How many wide receivers? How many field goal kickers? In fact, if the team was made up of all field goal kickers, these skinny kids that would break in two, the other team would run all over you, right? Or, in fact, a football team, 11 guys on the field, and every one of them is a heterogeneous set. You've got one quarterback.
Set of specialists, right?
That's correct. He's a specialist, and he's tuned. When we grow a quarterback, we grow him different than when we grow a offensive tackle. And if you put the two of them side by side, it wouldn't be difficult to recognize which is the quarterback and which is the offensive tackle, right? And that's the thing, is that anytime you want to optimize, you want a special purpose thing that is optimized for that thing. So it made sense to me, well, as I say, 12 years ago, that we ought to do that. That is, if we have a chip with multiple processors, they ought to be tailored to their specific needs. Now, the thing I was flying in the face of, which is, and now everybody seems to agree with me, and it's not me, I'm not the only one that thought this way, years ago, but the prevailing wisdom was too expensive. If you only have one, you can have multiple by going boom, 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 and it's much cheaper to do that. So I've been pushing heterogeneous forever, and now pretty much the industry seems to agree that heterogeneous is the way to go.
But it creates a lot of problems, right? Because it's easy when you have homogeneous cores to determine if I have a bunch of tasks, I can just put them on any core.
That's
right?
correct.
So now you've got all of these specialists, and I have all of these different tasks. So how do I deal with the fact that
You need a great
I have to
coach.
mix and match?
You need a great coach, see? The coach would never send in the kicker to be the quarterback, see? And so what you need is, and in fact, I've been advocating having on the chip some functionality that would determine when you need to send this task to which core. So in fact, this ACMP that I came up with, I guess it's about 6-7 years ago now, has a heavyweight core that is the one that is very powerful, and then these very simple cores. And the nature of the application determines where that task ought to go. And so I need some resource manager, and I like to think of it as what we call the runtime system, which typically is thought of as part of the operating system, which is way up here, have it right on the chip, getting information from the use of the resources on the chip to determine where to go. In fact, so somebody showed me this, so another analogy, they have this, where was I? Can't remember whether it was in Israel or whether it was in Spain. There's some GPS system, maybe you know about this, where it is so good that as you're driving along, they will monitor the traffic patterns on the alternate roads, and your route will be determined dynamically. So you're sitting in your office and you say, I got to get to such and such. So you get out the map and you plot the path. You get in your car and you drive there. There's an accident halfway. So you sit there for 3 hours waiting for them to clear the debris, right?
Right.
No, if you know the city, when you see the accident up ahead, you go around it. So you never have to wait, okay? Difference between doing it before you start, which we call statically, and doing it as you're doing it, adjusting, which we call dynamically.
And that's at runtime.
That's right, at runtime. In fact, that's what we call it. Compile time is done before you start. In fact, that's changing also. Runtime is as you're doing it, dynamically. So somebody told me that there's now a GPS system, you may know all about this, I don't, where instead of the path being determined by somebody at the factory who programmed the thing in the first place, there are sensors out there that are sampling, you know about this? Sampling
They'll dynamically route you.
That's right. They're looking at, well, if you go this way, you're going to get into a traffic jam. Maybe it's an accident, maybe who knows what it is. You go this way, there's no cars on the road. And they will dynamically adjust accordingly. And I think that's, that's the way to do it. And so I'd like to take that resource manager thing, put it on the chip. It's getting monitoring information from the chip. You know, this is busy, don't send it there. And have it adjust to which core gets the work to be done, you know.
Now, you also talked yesterday about what you called Morph core, which is a core that can morph between being a very complicated superscalar out-of-order machine with very
Heavyweight,
complicated
right,
branch
absolutely.
prediction, and you can dynamically morph this into, say, a set of smaller cores which are simpler.
That's
And this
correct.
seems to make a lot of sense because if I have one thread that I need to get done as fast as possible, I can use the big core.
Right.
ILP, I can exploit ILP. But if I have multiple threads and I have TLP,
Right.
then I can exploit that too.
And
So
the third thing is if you have no LP, then you can just use one of the Mickey Mouse pieces of it and let the rest of it just be powered off and
Right.
not waste energy.
be energy
That's right.
efficient.
Yeah,
Right,
that's
right.
Yeah.
But there's this kind of tension, right, with this configurability versus efficiency.
That's
can
absolutely
Can
correct.
you talk a little bit about that?
Sure. So the student who just finished his PhD last May, I guess it was, and he's now taking a job at Apple designing a processor. And he wanted to make every core on the chip a Morph core because you never know. He says, well, maybe you need all heavyweights. So you're absolutely right. Anytime you put flexibility in, you're going to lose in performance. My adjustable wrench thing, the adjustable wrench is flexible. You can use it instead of every one of those wrenches. You don't need 10 wrenches, one will do. But the 10, for any given task, the correct one of the 10 is better than the adjustable wrench. So anytime you introduce flexibility, you will not do as well as if you tailor it. So why is Morph Core a good idea? Because it provides a flexibility. What's wrong with it? You can't get the optimal performance for the task. So for example, if in fact you have IOP, that is, you need a heavyweight core, you don't have as heavyweight a core as if you designed it just as a heavyweight core. But it may be that you need 3 or 4 heavyweight cores at one point. How many do you design into the chip? If you design it into the chip, you've got these 3 or 4 heavyweight cores, and if you don't need it, you're wasting a lot of energy using it. In fact, our first work with ACMP was 1 heavyweight core. And with 1 heavyweight core, we discovered that, gee, there are times we need 2. We didn't have 2, we had 1. What Chabad, my student, would say is, see, if we had 2 Morph cores, then when we needed 2, we could have 2. Now, my view of the chip of the future is you're not going to have all Morph cores. I think he's wrong. You're not going to have all heavyweight Mickey Mouse. I think that's wrong. What you're going to have is some heavyweight designed as heavyweight so that you can get that ultimate performance, many Mickey Mouse so you can get that minimum energy.
Very simple course.
That's right. So yeah, I use the word Mickey Mouse, and Mickey Mouse equals simple, and it's fun actually to go to a conference now and have people who were never trained by me use the word Mickey Mouse, and my students sitting in the audience, they laugh. They say, "Wow, so he's adopted your name for it," which is kind of fun. But and then several Morph cores. So if you need more heavyweights than what you've designed as heavyweight, you've got this extra capability.
Right.
And so you like the flexibility, but every time you go with flexibility, you're going to lose on either performance for heavyweight or energy savings for simple. I'll use your term, simple, right?
But the key to doing this is to have a runtime system, right? That can monitor what's going on dynamically, right? It's a dynamic system where you're monitoring performance, monitoring power, monitoring the different applications, and trying to arrange things in the optimum way.
That's correct. In fact, in my talk yesterday, there was a slide where, and in fact, I didn't realize it until I prepared that slide. I was looking for examples of when the runtime system makes sense. And it turns out I know, it's amazing that I've been doing this for years and had no idea I was doing it. But I looked at the dissertations of my last 4 or 5 PhD students, and every one of them is doing some variation on, so the latest PhD, the lagging threads, that's monitoring. You've got multiple threads that are working concurrently on these multiple cores, and one is slower than the rest of them, and they can't all go forward until they all get to a certain point. So the monitoring says take the slower one and put it on the heavyweight so it'll get done, faster. And it's another example of this, of monitoring dynamically so as to provide the resources that are needed dynamically so to get the job done. It's kind of like the airplane is not able to take off until the passengers get on board. And the passengers came in on a different flight. So they have to get from the gate they came in to the gate that they go out, see? And there are a couple of passengers that are either old or slow or have a bum knee or something or other. And if we have to wait for them to get all the way, the plane's going to leave a half hour late. So what we do is we provide a heavyweight core. It's the cart that you put the person on and boom, he goes to the destination and he gets there in time. So you've used the cart. The cart is a heavyweight core to take care of this lagging passenger who would take too long to get there. So this concept of dynamically allowing the usage so that the whole job gets done faster is, you know, we do it every day at airports. Say. So it's.
And this is an example of, you talked about synchronization in a way, right? Because all the people who could be the threads are waiting for this slow thread, right? So we need to assign it to the fast core.
It's an example of synchronization. Synchronization, in my view, is the single most important concept associated with lots of, so parallelism is the fancy buzzword of lots of things being able to be done concurrently. At the same time, one has to synchronize at points in order to then move forward. And this is a very good example of synchronization. The plane can't take off till the, in fact, you've noticed, you know, somebody will come on and count the passengers in the seats, and they better have the right number, okay?
Right.
And if this guy was hobbling on crutches all the way, you know, he hasn't gotten there yet, you know. So they have to wait for that synchronization point where everybody's on board, and then they can take off.
Move forward.
That's right.
Right.